that was like on the wall. It wasn't water, it was gas.
All right, hey, everybody. So outside, you got a chance to do the warm-up, right? So you've been thinking about it and you did it. So I'm going to call some random people here. They're going to give the answer to... They're going to give the answer, excuse me. They're going to give you...
I took a picture.
Okay. So I want to hear from Nathan on the first one. What you get, Nathan? And remember, let's refresh our memory too here. What question are we asking on each one? We're asking, like for the first one, what were we asking? 2 to the what power equals 16, right? Remember that? That was like our big takeaway from yesterday. Evaluating the log amounts to you asking and answering that question. So 2 to what power equals 16? Nathan says 4, and he's right. Rock and roll. All right. Missy, you want to do the next one or the last one?
Sure.
Can you take the next one? Can you sure? It's not for the faint of heart, you know what I'm saying?
We're going to be, is it going to be negative or?
I don't know. Can't tell you. We're asking what 81 to what power gives you 3? You want to do the last one? I told you the second one's hard. What's the last? Yeah, go ahead. Tell me. 1. Yeah. Right? 5 raised to what power is 5? 1. Okay, so let's take a volunteer on the second one there because it's a little tricky here. Go ahead, Jesse. 1/4? Does that do it? See, 81 to the 1/4 is equal to 3. Is that right? Yeah, it's the 4th root of 81. Okay. Any questions, comments about that before we turn our attention to the homework we should look at real quick, I guess, huh? Okay. And you have reason to be proud because, I mean, really, 24 hours ago from this moment, you had no idea what a logarithm was. And now look at you. Just look at you. You're evaluating these crazy logarithms. Well done. I know. You should feel very smart. You've always wanted to know what a logarithm was, haven't you? You heard your friends talking about logarithms, and you were like, I want in on that party. You're invited, you guys, all of you, to the banquet. All right. What's that? No. To
the logarithm banquet.
To the logarithm banquet. Okay. Any questions on the homework? There are the answers, 2 through 11. 2 is an interesting one. I might want to say something about 2, but the other ones, are we good on? Yeah. We're going to have a quiz on this on Friday, all this stuff. And I'll have a lot more to cover today, so we'll see if I can do it in half an hour. I don't know if I can do it. Tell me if there's anything you want to talk about on the homework. Yeah, number 12 we're going to skip. After today you'll be able to do it. I apologize for assigning that. It's my bad. I'm glad. That means you were actually paying attention and looking at the homework. If you don't have a question on 12, then you should. Well, I mean, why don't you have a question on 12, people? You don't have to. We were going to do graphs today, but I didn't assign any last night today. Oh, yeah. I just hit the front, like the front of the front page. Yeah. But it's all good. So maybe we should say something about number 2 real quick. It says like what happens if you take the log of a negative number. This is an interesting question. Remember, like if you're taking log base 3 of -1, like it says there. If you're taking the log base 3 of -1, that amounts to asking what question? I'm asking this question here. What is the log base 3 of negative 1? Do you know the answer? Well, it's equivalent to asking what? 3 to what power equals negative 1? Isn't that the question we're asking? 3 raised to what power gives you negative 1? And what's the answer? Let's try some stuff. Let's say, to make some guesses, right? Like we've been doing in the last little bit here. Anyone have a guess for us? 1, 2, 3, those are probably not going to go in the right direction. 5? What'd you say? Actually, you're kind of right. I mean, you might need some complex numbers here. But if you were to try to make some guesses, I think most people's intuition would be like, well, maybe we need negative numbers or something. But negative numbers don't work, right? Because like 3 to the negative first, what's that? That's not negative 1. It's what? What would 3 to the negative first be? 1 over 3, right? Isn't 3 to the negative first 1 over 3? 3 to the negative second. 1 over 9. Those are getting small, aren't they? But they're not getting negative. They're still positive numbers. They're small, but they're positive. What else could you do? What about fractions? Does that work? 3 to the 1/2. What's that? That'd be the square root of 3, wouldn't it? Which is still, it's not a nice number, but it's positive. We're not, it doesn't seem like we're able to do it. There might be a good reason for that. Let me show you a picture of the graph of 3 to the question mark. This is what the graph of 3 to the question mark looks like. Have you seen it before? Yeah? Is that the graph of 3 to the question mark? And my question is, what, or 3 to the x, we might normally say, right? There's a graph of 3 to the x. And my question is, what can be outputted by this function? That is, what's the range of this function? What kinds of numbers can we get as a result of applying this function? We can obviously get numbers like 1 and 3 and 9 and 27, right? And we can get numbers like 1/3. What numbers can we get? What numbers can't we get? Yeah, I'm asking what's the range of this function, right? And the answer is 0 to infinity, isn't it? So can you get, well, 3 to the x, will that ever be negative 1? The answer is no, right? Will it ever even be 0? Could you have, like, if I asked you this question, hey guys, 3 to what power is 0? The answer is, I don't know, right? So this is interesting, right? This is, we would say, undefined. And so is the log base 3 of 0, right? So that brings it, we didn't really bring that into the discussion yesterday, but we want to start, at least start having that conversation, okay? So that was kind of an interesting problem. The others, are you getting right answers on those? You tell me. Okay. Homework solutions are leaving us in 3, 2, 1. Okay. So we ended yesterday by sharing these somewhat trivial properties, right? We said the log base b of 1 is 0 and the log base b of b is 1. You showed me that you understand those in the warm-up today because you did, what was it, log base 5 of 5? One of you guys did in the warm-up, right? And you said that was 1, right? I mean, so I think you understand those pretty simple properties about logarithms, even if someone didn't tell you them. One thing we'd like to say that we didn't get to say yesterday is this set of conventions that mathematicians and people in the world have agreed on, for the most part at least. Because we use the log base 10 so often, we like the base 10. We can use any base we like, but it turns out that we like 10 a lot, right? Because don't we like 10 a lot? It's the number of fingers I have, at least. I don't know about you. Okay. So we like 10s, and you know why, because we have a base 10 number system. So just like, you know how we write the square root, but we usually don't write 2, even though it is technically the second root, we usually omit it. Just why? Because of convention, because of history, because of, right? There's no special reason. It's just we use square root so often. So we use log base 10 so often that we usually just write log x. So if you ever see log without a base, you're like, wait, where's the base? Then you can assume that it's log 10. So if someone asked you, hey, what's log of 1,000? What would you say? What is log of 1,000? Remember, that's, if it doesn't say, what base is that? 10. So what's the log base 10 of 1,000? I haven't heard it yet. Remember what question you're asking? What question are you asking? 10 to what power gives you 1,000, right? And the answer is 3. Isn't 10 to the third 1,000? Now what's the nice thing about log here? Well, on your calculator, have you noticed that there's a log button? So try it now. Try typing in the log of 1,000 on your calculator and see if you don't get 3. Likewise, we have another logarithm that comes up lots and lots. It's called the natural logarithm, and that has log base e. Yeah, that e, the one that we studied, right? Well, because 10 to the third equals 1,000. Don't you agree? 10 times 10 times 10 is 1,000. Right. So anytime you see a log base e, we usually, instead of writing log base e of x, we use this shorthand, ln x, which sometimes you might say the natural logarithm of x, you might say ln x, or sometimes even people you hear say ln x. And because it's French, I think it's like ln instead of nl, right? It's like locally and natural or something. I don't know. Let's go get Mr. Jublin to help you say that for us. The French, man, we get a lot of good math from the French. So what would the natural log of, I don't know, what would the natural log of e be? What would you say? What question am I asking? What's the base? Doesn't say it, but what's the base? If it's ln, it's base e, right? So I'm asking e to what power gives you e? What is it? 1, right? And what about the natural log of 9? Now e is approximately 2.7, right? So it's like almost 3. What do you think this is? Without a calculator yet, the natural log of 9, well, if it was 3, what would it be? 3, what would the log base 3 of 9 be? Wouldn't it be 2? Right? So I'm thinking that this is probably, if we raise 2.7 to the second power, we're going to get pretty close to 9. So I'm thinking that it's probably 2 point something. So someone actually hammer that into your calculator. The other button you have on your calculator is the ln button, right? These are so important that you actually have 2 buttons on your calculator devoted to log and natural log.
How would you plug that in? Yeah, how would you do that?
It's right above your on button. There's a log button and an ln button.
No, yeah, but it's supposed to be like equal ln.
I'm just saying, so actually type in the natural log of 9 and tell me what you get. You should get approximately 2.197 or something? Okay. All right. Yeah, the answer here is not 2.197, but it is approximately 2.197. Okay. So now the question, of course, would be for you, what about evaluating logs of other bases? Can I do that on my calculator? Wouldn't you love to know? Yeah, okay. So I'm going to tell you. Okay. This is one way to do it. I think it's a great way to do it. Some of you actually have some newer calculators that have a log base feature on them. But this will work for any of your calculators, and I think this is actually, even those who have the feature, this might be a little faster and cooler. Okay. So let's like really stare at this and see what it's saying. If we have the log base, whatever we like, b of a, we can rewrite that as the log of a over the log of b. Well, what's the base? Here and here. Well, c, it says over there, is anything we like. So for example, here's one from the warm-up today. The log base 2 of 16 is equal to the log base, what's your favorite number? What's your favorite number? Jennifer, go ahead. 4 is equal to the log base 4 of 16 over the log base 4 of 2. Do you see that? Any number you like right here. Cool. Any number you like can go here. That's wonderful. But maybe if we're trying to use a calculator, that might not be helpful though, right? What base might you like instead here? If we're going to try and do this on the calculator. Your calculator doesn't do log base 2. And it doesn't do log base 4, then this is no help. What might you put here? You can put any number you want here. How about 10, right? By the way, what number should we get? What is the log base 2 of 16? We did it on our own in the warm-up. It's quattro, that's right. All right, so now actually type into your calculator. See if you get 4. Log of 16, close parentheses, divided by log of 2, close parentheses, and tell me if you don't get 4, okay? Could you also do the natural log of 16 divided by the natural log of 2? Absolutely, you should also get 4. Try it, try it, try it. If you're not getting 4, then because we know that this should come out to 4, log base 2 of 16. Did you get 4? Okay. Good. Here, try these. What's the answer to the first one up there? 4 again. All right. Okay, great. Didn't even need a calculator for that one. But you may use one now if you want to and just kind of check. Is it true that log of 81 divided by log of 3 is 4? It should be. Now these, maybe before you even reach for a calculator, what is this one going to be? Log base 20 of 565. That's not nice, but let's take some guesses. 20 to the first is 20. 20 to the second, that's 20 times 20 is 400. That's still not enough. 20 to the third. 20 to the third is 20 times 20. What's 40 times 20? But 400 times 20. 8,000. That's too much. So I think the answer to this one is going to be 2 point something. And what about this one down here? Do the same analysis here. 7 to the what power gives you 36? Well, 7 to the first, not good enough. 7 to the second is already too much, isn't it? So I think this is going to be 1 point something. So, you know, on your calculator, actually tell me what those are. So do the log of 36 divided by the log of 7.
Yeah, how do you plug it into?
The way we just said, use the change of base formula I just used, right? Okay. You do the log of 36 divided by the log of 7. 1.84 on the last one there. And what about this one here? We'll do log of 565 divided by log of 20. That one too.
It's from Greece. 1.6 is what? Damn, I got it wrong.
2.115 approximately is what we're getting here.
I got one.
Make sure you're typing it in right. Are you typing in parentheses, 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 parentheses?
It already gives you one of the parentheses. Like it already.
Yeah. It gives you the first one. It's trying to help you, but that might hurt you if you add another one.
I didn't close
What?
it. Okay, now I got it.
So did you get those 3 answers?
Oh.
we'll skip this. Oh, this is worth talking about a little bit here. Okay. Oh man. Silly fire drill. Okay. Let's see if we can do this. Two properties. I'm going to put them in a box, and these are two more properties of logarithms that I need you to know. These are called. Well, I can't tell you what they're called yet. I haven't told you yet this. I've been holding out on you. Logarithms, the logarithmic function that we've been dealing with, and the exponential function, you know, 2 to the x and log base 2 to the x, 2 of x. Right? These two functions have a very, very special relationship. They are, no, they are inverses. And so everything that you know about inverses, right? Can you think of lots of things we talked about when we were doing inverses? How you find inverses, the reflection property, the inverse composition rule, all the things you might know about inverses come to bear on our knowledge of logs and exponents now. Are you ready? So this is one property that comes out of that. This is the inverse composition rule. You remember that rule? That if you take a function and compose it with itself, that you always get x. You remember that? In either direction? Don't write down all the words here, just the thing in the box here. All right, so if we have this function, here I'm boxing something else here and here. In this function, I'm saying that these are inverses, and so if you put one of these functions inside the other, then you'll get x every time. Same with the other way around too. If you put this into here, you get x. You can kind of think about these as kind of canceling out even. And they do, like it says down below. They kind of undo each other. So I'll show you here what I mean, okay? So for instance, 10 to the log 2, what would that be? Well, without your calculator, let's see if we can get this. 10 to the log, what's the base there? It's base 10 even though it doesn't say, right? So if these match, this is 10, this is a log base 10, then what does this say here? This first property is maybe the one to go for. What does it say? If you have the log base, excuse me, the second one. If you have something to the log base, that same thing, of x, what do we get? What's the answer supposed to be? X, right? Which is just, in this case, 2. So like I said, in some senses, I think it's a little sloppy to say it, but in some senses, this 10 to the log base 10 of whatever, it kind of all cancels out, right? That's a direct application of that second property over there. These are called the inverse properties. Yeah, I mean because it's a log. We don't normally write the 10, but it is a 10 if you want to write it in. If you wanted to put this in a calculator, you just do 10 to the log 2 power, and you'd get 2. Promise. All right, the second one there is a little trickier. We're going to use that first property if we can. Log base 3 of 9 to the x. Now in this property over here, if these two numbers are the same, boom, we're done. It's just this. It's just that number up top, right? These two numbers are not the same though. That's a little bit of a sad story for us. But maybe we can massage this a little bit, get it to be what we want it to look like here. 3 and 9 have a relationship, don't they? What's the relationship? Way of rewriting 9. 9 is also known as 3 squared, right? So I might write this way. And then what's 3 squared to the x? What do we do with powers when we have a power of a power? Yeah, we multiply. So log base 3 of 3 to the 2x. All right, now we can apply this property here, right? We have the log base whatever of whatever. These match now, and so what's the final answer? These can kind of cancel out. We're just left with what's up here, which is 2x. Okay, I know it's still a little unsettling. Let's do a couple more just like this here. All right, this one's actually the one we already did, so forget that. What about e to the natural log of 6? What would that be? No, don't ask your calculator. It'll get it right, but don't ask it. Yep. What is the natural log? That's the log base. That's also known as the log base e, right? Of 6. So what does that come out to be? Yeah, they cancel out, so you just get 6 is our answer there. And what about this guy down here? It's just 5. Let's let Jonathan answer all the questions. That'd be good. All right. It is just 5. It also should kind of make sense. Let's just stop for a second and make sure we understand that why this actually kind of makes sense too, right? Well, because I just don't believe anything you say, Mr. Chase. You have this property that this like 4 and the 4, they match, and so therefore I know that like it kind of cancels out, and it's like a 5. Okay, I just trust you. But also, let's just ask the question that we originally asked. 4 raised to what power gives you 4 to the 5th? Duh, right? It's like when you say it that way, it's like we're kind of giving you the answer, right? If I were to write log base 4 of 1024, you'd be like, ooh, that's kind of a hard problem. 1024 is 4 to the 5th. Did you know that? Did you know that? Okay, well, now you do. Okay, so if I gave you this problem, you'd be like, ooh, that's hard. That's hard. I don't know what the answer to that is. But if I were to re-express 1024 as 4 to the 5th, what have I done? I've basically like given you the answer, haven't I? Or if I say, hey, what would I have to raise 4 to get 4 to the 5th? Well, of course the answer is 5. It's almost not even worth saying. So I know this looks complicated. This rule is terrible. Both of these rules look kind of terrible, but really, they're not saying something very profound, really. They're saying that none does it. We're going to skip the inverse stuff right now, that stuff right there. I'd love to show, I want to show you one graph before we leave, okay? I'm going to try and show you one graph before we leave. Okay, so here's the big idea. Remember, these are inverses. The exponential function and the logarithmic function are inverses. And so here in blue, you see the exponential function. Maybe this is like, well, you know, y equals 2 to the x or something. One of the ones we might have graphed on our quiz the other day, right? The logarithmic function, y equals log base 2 of x, I claimed these are inverses of each other. And so the inverse composition rule is true, right? Everything you know about inverses is true. Do you remember this property? That when you graph in blue the function, graph the red function, the inverse function, you get a reflection over the line, this diagonal line, y equals x. Does that ring a bell? Okay. Which makes me think, if we want to graph a logarithm, the exponential function always has a horizontal asymptote, doesn't it? The exponential function always had this nice horizontal asymptote. Well, what do you think will a logarithmic function always have? It'll always have a vertical asymptote. Do you see it? Normally, we have a horizontal asymptote on the exponential function, y equals 0. On the logarithmic graph, we always have a vertical asymptote, x equals 0, or wherever it might shift to. Right? The domain of the exponential function, do you remember what the domain of the blue function is on the quiz? It was a freebie on the quiz, wasn't it? What's the domain of any exponential function? Yeah, it's always all real numbers. So what's the range of the red logarithmic function? It's the same, right? It's the range is, yeah, because the domain range flip, right? What's the range of the blue function? What can y be? Remember what the range of an exponential function is? Greater than 0, right? So like 0 to infinity, we might say. What's the domain? That was the range of the exponential function. What's the domain of the logarithmic function? What can x be in this picture, in the red picture? These are switched, right? So it's greater than 0, right? So the range of the blue function, the exponential function, is 0 to infinity. The domain of the logarithmic function is 0 to infinity. You see it? And we already talked about this today. This is our like, we haven't seen in a while, a function that you can't plug things into, right? The logarithmic function is a good example of that. The domain is limited, right? You can't plug, we talked about this when we first came in. You can't plug in negative numbers. All right, thanks to the fire drill, we didn't get to do nearly as much as I wanted to. Do what you can on the homework. I would like you to graph some of these things, and we do have a quiz on Friday, so we're gonna have to kind of repair your knowledge a little bit tomorrow. Make sure you're good at graphing these and comfortable, ready for the quiz. So I come up to you and I ask you what your birthday is. Say. And then what's the probability that her birthday is that day? 1 out of 365. That's the answer, right? Just 1 out of 365. Right? Now, this is a different question. What is the probability that both of you have the birthday June 2nd? That is a little bit of a different question. That's the 1 out of 365 squared. Because I picked this up. So, what about the probability of 3 people? So 1. So you roll over the 3 numbers. Yeah, it doesn't have to be anything. The other person has 365. And so the number. Yeah. So would that be 365? That's 1 over 365 squared. Okay. What's the probability that 2 people don't have the same birthday? I walk up to 2 of you. What's the probability that 2 of you don't have the same birthday? It's high, right? Obviously. 364. Yeah, 364 over 365. Okay. How many? Okay, so that's just with 2 people. Now, in a room of like 10 people, how many pairs can you afford? Right, because for every pair of people I pick, the probability that their birthdays don't match is 364 over 365, right?
No, this is the question.
So that's the probability that for any given 2 people, their birthdays don't match is that. But then the question is, if you have 10 people, if you have 10 people, how many different pairs do you have? We want to multiply by that number. Or actually, there are no 2 people that share a birthday. So this is the probability that a given set of 2 people share a birthday.
Oh, that's not my class.
Yeah, so this is the question. The new question if you didn't know. what's the probably in a room of 10 people, there are no shared birthdays. So for any given 2 people, we have it figured out. In a room of 2 people. So the question is, how many pairs are there among 10 people? Do you know that? Okay, let's do it 3 people, right? No person shares a birthday. So here's person A, B, and C. The probability that these guys don't share a birthday is 364 over 365. The probability that these guys don't share a birthday is 364 over 365. And the probability that A and C don't share a birthday is 364 over 365. So that would be 364 over 365. So the third, that happens to be 3. I'm not big fan of that though. What is it for 4? Is it that it's not going to be necessarily 4? I'm not sure. How many different pairs can we form from this? Yeah, how many different pairs are there?
Playing math games.
There's so few that you can just enumerate, but A and B. Your BA is the same thing.
Yeah.
So this is the probability that in a room of 4 people, no one shares a birthday. What's the probability then in a room of 4 people that someone does share a birthday? That someone, not everyone, just that there exists a pair that shares a birthday. Well, careful. That's one pair of people, right? I said, what's the probability that what's the probability that in a room of 4 people that we do have shared 2 people's same birthday? We do 2 people, yeah, and or more, or 3. I was just curious. Like if I walk up to 4 people, what's the probability that any 2 of them have at least any 2 of them have the same birthday? That there might be a shared birthday. Careful. Well, the reason we did this problem first is because this makes it easy. What's the opposite of this happening? 4 people do not share, none of them share a birthday. It's the question we're just asking, right? So, it's this, right? The probability of a shared birthday is 1 minus this, right? Because whatever this comes out to is some percentage. So it's the other thing that could happen, right? Where you're comfortable with 1 minus, right?
Like what is the one? It's like the whole.
Yeah, so the probability of anything happening at all is 1, right?
Okay.
Like, what's the probability you walk up to 4 people and they're like, they have birthdays? 1. Right, it's a 100% chance that happens. If the total probability of everything that could possibly happen happening is 1, and the probability of them not sharing birthdays is 364 or 365 to 6. So the probability that at least 2 people do share a birthday is the stuff you didn't count, right? Right? It's like someone asks me like, the probability of a head is 75% on my weighted coin. I have like a special coin. What's the probability of getting a tail? Well, of course it's 25%. It's 1 minus 75%, right? The probability of the other thing happening is called complement. So in a room of 4 people, the probability that you get shared, 2 people share a birthday is that. So in a room of like 10 people, you still have to figure out how many pairs that is, right? So you need to build up some mathematics here to help you, because it's hard to come up with the number of pairs, right? Among 10 things. Among 10 things. How would you do it? You come up with a mathematical way to do it. wait, hold up. I want to make sure you're hearing. Okay, so 9 times 10. So all of them have that, except,
Yeah.
okay.
And then your new repeating period, so we divide by 2.
Very good.
Yeah, it gets you 10.5.
Yep. Okay, so in a room of 10 people, the probability that someone shares, and actually I'm kind of curious what this is, right? What is the probability of 2 people in a room of 10 sharing a birthday? We have to do it. Right, because I'm curious, this is an interesting question. What's the probability of, in a room of 400 people, what's the probability of there being shared birthday?
1 people. So you